Hello all, good evening and welcome back to evening sessions, day 4. Good evening, Sri Krishnan.
Yeah, thanks, Shashi.
We have Ranjita on stage along with Dr.
Sure, yeah. So good evening, everyone, and a warm welcome to the final session of the 9th edition of the IEEE International Conference on Cloud Computing in Emerging Markets. So I will co-chair this session with the distinguished Dr. Gopal Pingali, who's the founder CEO of CEARG and former vice president at IBM. This session, we will start with a keynote from Dr. Ranjita Bhagwan from Microsoft, followed by a tutorial session by Dr. Joseph Spillner and Panagiotis Kikopoulos from the Zurich School of Applied Sciences. We will follow that by acknowledging the main people who work for the success of this conference. And we will also talk about next year's plans for the conference. And finally, we'll have the awards ceremony, where we will announce the best paper awards, the jury's choice for the student POC and the Technobiz showcase plans. And then we will bring the curtains down on this year's edition of the CCEM. So I'll now request Dr. Gopal to introduce Dr. Ranjita. Over to you, Gopal, and welcome, Ranjita.
Thank you. Yeah, thank you, Krishnan. And Krishnan is certainly the distinguished chair here for this session. He's the distinguished engineer from IBM and the CTO of the Cloud Center of Excellence. So my pleasure to welcome Ranjita Bhagwan from Microsoft Research India to be a keynote speaker at CCEM. So welcome to CCEM, and we are really delighted to have you with us, Ranjita. And brief introduction. Ranjita will be talking about using data to build better cloud services. And she's a senior principal researcher at Microsoft Research India. And her research has been predominantly on problems related to networked and distributed systems. She has been working in this area for more than a decade, and especially now applying machine learning to improve system reliability, security, and performance. And we should all give her applause because she recently received the Best Paper Award at Usenix OSDI 2018. And so it's great to have you with us. And Ranjita has also chaired multiple top-notch conferences in systems and networking. And she received a PhD in computer engineering from UC San Diego, University of California, San Diego, and BTech in computer science from IIT Kharagpur. So without further ado, I'll hand the stage to Ranjita, and we all look forward to hearing her talk. Welcome, Ranjita.
Thank you. Thank you so much, Gopal. Thank you, Sri Krishnan. So I will share my slides. Just let me know when folks can see it. Every new system takes some time to learn.
There you go. All set.
Okay,
Looks good.
Okay. Thank you so much for inviting me to give this talk. It's a real privilege to be here today virtually. My talk is going to be on using data to build better cloud services. This is, of course, a joint work with a lot of people all across the board. And I would especially like to thank all my collaborators, engineers, researchers, interns, etc., research fellows who work at MSR India in actually helping me do this. Could somebody give me a shout out when there are about 10 minutes left so that I know when to stop? Thank you. Yeah. Okay. I'm going to start by talking about why this has become a big research topic and a very relevant research topic recently. This is mostly because we moved significantly over the last decade from boxed products to building cloud services. Now, as we moved from boxed products to cloud services, there were some shifts in technology, and I'll talk about two shifts specifically. Firstly, when we had boxed products, like you bought Windows on a CD, right? You would put the Windows version on your machine, and then you would take months or maybe even years to come up with the next, or to buy the next CD or the next version of Windows. So there was very little similarity between those two. But now with cloud services, you have multiple deployments even in a single day with continuous integration, continuous deployment, right? And because of that, there is an opportunity, which is that we can learn from previous deployments of what went right, what went wrong, etc., to drive our design decisions for the next deployments. But at the same time, there's a challenge. And the challenge is that there is this non-determinism now. When something goes wrong, which version do we blame, right? Because all these versions are so close to each other, it's very difficult to put blame on one without knowing details about the other. So this is one. The other thing is about rich telemetry. Earlier, when you had these box products running on these remote machines, remote desktops, you could not collect telemetry. And even if you did, it was opt-in. People had to say, yes, send the information to Microsoft, etc. Right? But now the cloud is the main thing. Everything runs in the cloud. And because of that, we've been able to put together great infrastructure to do monitoring and get telemetry. So that's the opportunity. We have a lot more deployment data in terms of logs, exceptions, error messages, etc. But at the same time, the challenge there is the problem of data. When you have this huge amount of data, how do you actually go about finding this small needle in this ever-growing haystack? And that's what our research concentrates on. Now, if you look at the typical software development lifecycle of a cloud service, you have four main stages. The first is development. Next is build and test, build the code and test it. Then you deploy it. And then post-deployment, you have monitoring, alerting, etc. Now, in all of these phases or all of these stages, there are all sorts of problems that come up. Firstly, misconfiguration is just too common, and it happens all the time. Secondly, it takes too long to root cause service disruption. Thirdly, deployment can take too long. So there are all these are just examples. There are lots of such problems that happen. So at Microsoft Research India and across Microsoft, we've been working on a project called Sankie, where the idea is to use all this data that we collect, telemetry that we collect from our systems, to build tools that will help developers, help engineers in this whole software development lifecycle. So this is a list of tools that we have built and analyzed, and a lot of them are being widely used within Microsoft across services like Office 365, Bing, Azure, etc. And I will concentrate on two of these analyses that we've built, tools or analysis that we've built in this talk going forward. The first will be on finding misconfigurations. And the second will be a root cause analysis tool that we have built. So the first, like I said, is Rex. Rex is a tool that we've built to prevent misconfigurations using correlated change analysis. And this talk is based on a recent paper that we published at NSDI 2020. Consider the following scenario where a developer is tasked with the job of renaming a microservice, say from old microservice to new microservice. And for that, they have to make a change in one file. But at the same time, they also have to make changes in some related files. So in this case, when you make a change in registry entry.xml, you have to make those changes in 3 other files as well: load balancer.xml in ITAR, load balancer.xml common, and firewall rules.xml. Now, say the developer who's doing this is new and doesn't really have this domain knowledge that all 3 have to be changed. So let's say she only changes 2 of them and does not change the firewall rules.xml. Now, this can actually cause a service disruption, because all the firewall rules essentially are punching holes in, and they're still punching holes for old microservice and not for new microservice. So that causes all the traffic to get dropped by the firewall and therefore a service disruption. Now, this is not an artificial example. This is taken from a situation that actually happened within Office 365. So this is an example of what may happen. And so a small missing configuration change can also cause a serious outage or disruption. 1 second. Now, this is not, this is a generic problem. This happens across, all different types of services, across different types of applications, can cause security issues, service disruptions, etc. Now, why is, and that's generically configuration management, not just the correlated changes, but correlated changes is a big part of it. Now, why is configuration management really so difficult? First, there are all these dependencies and correlations that I gave an example of, which emerge organically. And these are different for different services. There is no uniform language or spec that you can specify. And that's why no compilers exist for checking the correctness of configuration. The other problem is that the amount of configuration in a cloud service is just continuously increasing. If you look at this graph, this says for Office 365, over a period of 6 months, the number of XML files has more than doubled. Right, so this gives you an idea. These XML files usually contain configuration. So this gives you an idea of how much growth there is in configuration. So when you have so much configuration, it's really hard to document these correlations as they keep changing frequently. Now, we are not the first people to this problem. There's a lot of work in this area. So there's holistic configuration management at Facebook, multiple research papers, etc. But one thing common to previous work was that all of them expect some manual input, right? But whenever you have manual input, it becomes a challenge that we have to scale to thousands of configuration files, millions of parameters. It's very difficult when you have a system that requires some manual input. So we said, look, we have to design something where there is absolutely no manual input. And that's why we came about with Rex. Now, Rex uses a two-step process. And the first step is particularly simple by design. It's called change rule discovery. And the second step gets a little more complex, which is called change rule refinement. Now, I will describe both of these in a little bit of detail. In change rule discovery, you are trying to detect correlated file changes. So when things change together. This is particularly reminiscent of association rule mining, frequent item set mining. And so that's essentially what we do. Now the input are commits. So we get commit inputs from our Git backend. And that's the great thing that we have now. We have Git and other version control systems that store years of history. So we have all these commit histories. And this goes into FP growth, which is an association rule mining algorithm. And out comes rules. Now, this is heavily influenced by work done by my colleague Tom Zimmerman, who over the last 15 to 20 years has been working on correlated file changes. Now, what does a typical change rule that we've learned look like? So this says that when you change file X, content filter /spam rule.xml, you need to also change file Y, which is post content filter spam rule.xml. And we have a support and a confidence for this rule. Support is the number of commits in which both X and Y are changed. And confidence is the number of commits in which both X and Y are changed divided by the number of commits in which X changed. Okay, so these are just very, very typical metrics. And the higher the support, the higher the confidence, the better the rule. Okay. Can someone just tell me that they can still hear me?
Yes, loud and clear.
Great, thank you. All right. Now, we ran this change rule discovery module. We deployed it on about 50 Microsoft repositories for about 3 months to see how it worked. This was the first phase of our deployment. And the way we did it is when you create a Git pull request, if you change only one of the files for which we have a change rule, we also have an automated suggestion or an automated comment like this. So this says, consider editing this file because you edited these files, and the pull requests which edited both sets of files is like so, right? And then we suggest that people give us some feedback. Of course, nobody gives us feedback, but that's typical of such systems. But we have designed a way to get feedback, implicit feedback. So we give this comment, but we realized that change rule discovery, it does a good job, but it's also a very coarse-grained approach, because if you even just put a comment in file X, we'll put this comment in the, we'll put the suggestion in the pull request, which was giving lots of false positives, sometimes getting, making developers irritated. So we said we have to do something better, and that's where change rule refinement comes in. What is change rule refinement? Essentially, at a high level, we say that if file X changes in a particular way, only then suggest a change to file Y as well. Now, here's an example to explain why, how this would work. Now, let's say in file X, it's an XML file, you update the version number, okay, like so, highlighted in green. And when you do that, only then you change the same version number in a reference in file Y. But if you add a new reference in file X, you don't necessarily change anything in file Y. So the idea is to discover these kinds of changes and these kinds of relationships. So what kind of change in X leads to change in file Y? And that's how we design change rule refinement. Now, the main piece in change rule refinement is an algorithm or a generic technique called inductive generalization. Now, what is this, right? Let's say we input all these commit histories, and there are 3 commits in this example, where you're changing just the value within this command config tag. Enable IPv6 in one commit, add root in the next, and add subnet NAT in the third. Okay. Now, what we want to do is learn a generalization, or in common parlance, we want to learn a regex in this case, which captures all these changes. Now, a very simple regex to learn would be star, which would capture everything but everything else in the world also, right? So that's not a very good one. We could also learn a regex like this, where you just learn the network tag on the outside and star for everything else. But this is also not great. The best generalization is the third one here, which is the most specific generalization we can learn from these 3 inputs, where you learn that the outside is always the same. The network, whatever is within the network tag is always the same. And it's just the command config which changes. So you learn the star only for the values within command config. So that's the most specific generalization. And we do this by using an algorithm called anti-unification, which is specifically designed for code which has tree-like structure. And every configuration file has a tree-like structure. So that's why it's an automated match. First thing we need to do is build a differencing engine for code commits. So when you do the differencing for each of these changes that happen, we learn a tree. And from these trees, we feed it to the anti-unification algorithm, and it spits out this generalization. Details of this are in the paper. I don't have time to go into it. So I've spoken at a high level about generalization, and finally about refinement. And finally, we have these enhanced rules. So we have, when you change file X, you change file Y from change rule discovery. And now you have these sets of generalizations which say, when you change file X in just these particular ways, only then you change file Y. So you make that suggestion only when these generalizations are met or matched by the commit. Now, I want to talk about the timetable of our deployment of Rex. So this is not just a research project. It's widely used across Microsoft. Currently, about 1,100 repositories are actively using it across all Microsoft major services. So in February of 2018, we started working on Rex. In June of 2018, we deployed change rule discovery on 50 Microsoft repositories just to see how it did. In October of 2018, we realized, okay, we need to do something better to reduce the false positives. And in July of 2019, we actually deployed change rule refinement. Now, this is a slightly old slide. We deployed this on 400 repositories with change rule refinement as well. And this the system processes more than 1,000 pull request updates per day. And we had made about 5,000 recommendations which developers found relevant and they acted upon them. Currently, this number is even higher. Now, a very important thing we learned while designing Rex and deploying it is the evaluation of it, and how do you actually evaluate such data-based suggestions. So this slide talks about the evaluation metrics. Let's say that our technique detected 100 bugs, and I'm using the term bugs here because this generalizes outside of just Rex. So let's say we detect 100 bugs, of which 80 are true positives and 20 are false positives, right? Now, this means that the precision of our model is simply 80%. But if you look at the 80 true positives, 72 of the true positives, let's say, are already changed by the dev. So in the case of Rex, you say when X changes, Y changes 80 times, which are right. But in 72 of those cases, the developer has actually made that change already. So you don't make any suggestion in those. Only in 8, you make suggestions, and those are actually very valuable because that's where the developer has missed making the correlated changes, right? So we found that roughly 90 to 95% of the cases, the developer does not forget, but 5% where they forget is very important to point out, right? So this gives us really a deployment precision of 8 true positives, which are really useful, divided by 20 plus 8. You have to count all the false positives because those are suggestions you'll make anyway. So that means your deployment precision is significantly lower than model precision. And this is fundamental to such approaches. So when you evaluate these techniques, you have to evaluate it both as with model precision and deployment precision, depending on how you deploy it. So here are some results for about 6 repositories that we deployed this on. The model precision is high, 75% to 100% as well in some cases. But the deployment precision, as you can see, is significantly lower. So with change rule refinement, we get deployment precisions of between about 16% to even 50%. But without the change rule refinement, the change rule discovery is more generic because it spans across multiple file types, but you get lower values of precision. But so this shows you the value of both change rule discovery, which is more generic, and change rule refinement, which improves the precision for specific types of configuration files. So that was Rex, and now I will be talking about a post-deployment tool that we've built, which is Orca, a root cause analysis tool. This was a paper that we published in OSDI 2018. And also, this is also deployed and being used within Microsoft. Now, before I actually talk about what the tool does, I want to explain the problem itself because it's not a very familiar problem right now. So there's different stages of the software development lifecycle. There's code, build, deploy, and monitor. Now, in monitoring, let's say an alert gets fired that there is a bug, the service is getting disrupted, do something about it. What usually happens is that an on-call engineer is woken up late at night, maybe, and told, go and find the buggy commit and revert it as soon as possible, right? So they have to do this really, really fast if they can. But one thing to note here is this is not traditional debugging. Okay, it's not like the on-call engineer has to debug the code. They just have to find the buggy code and just revert, right? Take it out of deployment, essentially. But it turns out that this whole action itself, identifying the buggy commit, can take hours or even days in some cases, because the on-call engineer is not familiar with the code very often. And more importantly, there could be hundreds of commits being made even in a single day. I know it sounds strange, but I'm sure folks on this call can relate that these code bases are changing at crazy frequencies. Okay, so when you have hundreds of commits, how do you pinpoint one of those buggy commits? So that's where Orca comes in. Orca is essentially a search engine to try and localize the bugs to the right commit. Okay. Now, the design of Orca is based on two key observations. The first is that there's a textual similarity between the symptom and code changes. Now, let me explain what I mean by this with an example. Let's say you are running an email client and you see an error. Oh, this operation is not supported for type mail ID. Turns out that on the server side, a function get mail session was changed. A Boolean variable was added in the definition. The Boolean variable was called return mail IDs. Okay. This is the root cause. Support for data type mail ID was added on the server side, but for this specific client that you're using, it was not added. So it was not found in testing because you can't test every client. And so for whatever reason, you didn't find it. But notice that the word mail ID exists both in the error message and the code change. Okay. Now, turns out you may wonder, how can this be true so often? But what has happened over the years is that these cloud services have really invested in rich monitoring infrastructure. So these error messages, alerts, etc., have gotten really specific and have really good indications of what could be the problem. For instance, there are thousands of active monitors across Exchange Online, Microsoft's email service. The second observation is that the buggy commit may not be part of a symptomatic build. What do I mean by this? Let's say these are all developers and they're making commits to multiple builds, and build 4 is the latest build. And let's say a bug shows up on build 4. Now, let's say that a commit C to build 3 by this dark green developer actually caused the problem, but the symptom shows up only later in build 4. So you have to be mindful that something that symptomatic in the most recent build could actually have been caused by a commit to a previous build. So these are a couple of observations that have led us to the design of Orca. Orca is a search engine for localizing bugs. Gopal, can you tell me how much time I have left? I'm sorry, I don't have timer.
Yeah. So we closed the talk at 6:15, so that's another 17 minutes. So I would say you should wrap up in another 7 minutes or so.
Sounds good. Thank you. All right. So what is Orca? Orca is a search engine where an on-call engineer can put in anything as a query. They can put in customer complaints. They can put in alerts. They can put in log error messages, exceptions. Any sort of symptom of a problem can be a query. Now, what it searches on are documents. So what are documents for this this custom search engine? Number one is code differences. Okay, so to build these code differences, we have to do something that we call differential code analysis on the abstract syntax tree of the code changes that have happened for each commit. And the second thing that we search on is a build provenance graph. So like I said earlier, there are multiple builds. And so you can't just search on the latest build, you have to search on previous builds as well. And that's is captured in the build provenance graph. And thirdly, for ranking, we use commit risk estimates. And this uses machine learning classifiers to determine how risky these commits are. So this is a secondary ranking function we give to Orca. Let me talk in a little bit of detail about differential code analysis. So the code on the left is the code as it existed before, And the code on the right is the addition that was made, and it's highlighted in green. Now, we not only capture the textual changes, which Git gives us automatically, but we also have to capture the method that has been changed, the class that has changed, and also the namespace that has changed. So in this case, you capture the words storage, connection, and begin TX, because this is the namespace, class, and method. Now, the custom tokenizer extracts important keywords from all of these. So in this case, it will extract storage, mail, TX, mail filter, multiple things. So from the textual changes and from the set of classes changed, methods changed, and namespace change, we extract these tokens. Okay, and that for a particular commit creates the corpus that we search on. The second thing is the build provenance graph, and I don't have much time to go over this, but let me try. So builds are actually deployed in terms of rings or stages. Different people call it different things. So a ring is a set of machines on which one build is deployed. So ring 1 could be the smallest ring with, say, 100 machines or so. Then ring 2, you deploy on a larger set of machines, say 1,000. Ring 3 could be 10,000, and so on. So in this graph, the x-axis will show time. So let's say the first ever build was in ring 1, 1.0. Then you make some commits to that. Then you go to 1.1, 1.2, and so on. At some point, an engineer decides, okay, build 1.0 has baked long enough in ring 1. Let's promote it to ring 2. And then it gets promoted to ring 2. And then at some point in ring 2, you notice a bug and you put in a bug fix. But you also have to backport this bug fix to ring 1. And that creates another build, which is 1.3, and so on and so forth, right? So this build graph can get quite hairy. And then let's say there's an alert in build 3.2 that, oh, something is wrong. Then it's not enough to just search the commits in 3.2. You also have to traverse this build graph in a certain way to make sure that you find the problem. Commit risk, let me just skip this slide in the interest of time. So we've evaluated Orca with a manually curated list of about 48 code-related incidents. Now, you may think 48 is a small number, but we just had to manually figure out these 48, figure out the root causes, because on-call engineers don't have time to document these really well. And the key metric we used is mean reciprocal rank, which is given by this formula. It's quite simple, actually. The higher the mean reciprocal rank, the better the system is. The closer it is to 1, the better the system is. The table here shows the top 10 recall and the mean reciprocal rank for Orca for these 48 code-related incidents. So by just using the diff on AST, in 33 out of the 48 cases, we found the right root cause within the top 10 results that Orca returned. When we added build graph, this recall went up to 37. But at the same time, the reciprocal rank dropped from 0.44 to 0.38, which was not good. But then we added this commit risk estimate that I briefly mentioned. Then our recall stayed the same, but we regained most of the loss that we had in our reciprocal rank. So a mean reciprocal rank of 0.42 is not bad at all. It's close to a rank of 2 in the list of commits that the tool gives back. See, the other thing we evaluated is the amount of effort that the on-call engineer has to make to figure out the buggy commit. So we brought this down by a factor of 3. In many cases, they had to look at hundreds of commits to figure out the right commit, or go and talk to multiple people to figure this out. And with the Orca search engine, they could actually figure it out much faster. And it was really great listening to some of them coming back to us and telling us that they found the tool very useful. So that sort of summarizes or ends my talk. But I would like to end with the lessons that I've learned by doing this. I've been doing this for about 3.5 years now. The first thing I learned is simplicity really helps. So either use simple ML or none at all, right? Things like decision trees, random forest, logistic regression, etc. have worked really well for us. But as data increases and as the cleanliness of data increases, I think we can start using deep learning models, and they will become much more practical. And we have ongoing research in using deep learning models for such applications. The second is to choose the right applications to target. So, for instance, commit risk was okay for doing this ranking model in Orca. It's a soft use. It's a secondary ranking function. But we also tried to use it to fast track commits. When we estimated the risk was low, then we should fast track it. But it did not work well for that at all, and we pulled that effort completely. So that was a big learning experience for us. The third point, which is I think the most important point, is that user experience is key. So make suggestions. We have to use the right language. Don't say, hey, you forgot this. Perhaps you forgot it. Why don't you take a second look? It has to be gentle. And also, we need to ensure that engineers understand that these are data-driven solutions. There will be false positives. Once we set those expectations, engineers really saw the value in what these techniques provide. So that's it. That's my talk. I spoke to you about 2 of the techniques that we have built, which are currently deployed widely across Microsoft. There's more work that we've done in this area, and a list of them is mentioned here. We also have a website. You can just search for Sankie Microsoft Research. It should show up. Thank you very much, and I can take questions now.
Thanks a lot, Ranjita, and let's all thank Dr. Ranjita Bhagwan for a great presentation, really talking about how we deal with this new world of cloud and how we deal with these kind of problems. I'll open it up to questions. I'll come back with some questions, but why don't we open it up to the audience first? Any questions, anyone? If you can raise your hand or type in your question. Yeah.
So do I actually see the question here?
Yeah. If they type in, we'll start seeing it, but we'll also bring them on to the stage if somebody has a question.
Maybe while we're waiting for that, if I may, I have a question, Dr. Ranjita.
Sure.
So like Gopal said, very captivating talk. My question is perhaps partly philosophical. So Edgar Dijkstra once eloquently stated that testing can only show the presence of errors or bugs and not their absence. And you described the REX framework and its the change rule discovery mechanism that seemed to largely fall under the category of detecting the presence of bugs and not its absence. But perhaps the differential code analysis that you explained in Orca and the textual similarity detection, such to the extent I understood, could perhaps be formally extended to in the prove correctness area, right? For formal correctness proof rather than merely detecting bugs. I'm asking this because, like you pointed out, code change rates are massive. You said the number of configuration XMLs in Office 365 doubles every 6 months, and we all know that the Linux kernel code almost gets completely rewritten every few years. So I know this is easier said than done, but shouldn't reliability research like the one that you're doing kind of pivot in the direction of formal code correctness and verification of code rather than stopping at innovatively detecting the presence of bugs?
Yeah, that's a great question. So I think techniques and techniques like what I have described here go hand in hand. They are complementary. Both are required, and both have their pluses and minuses. So the minuses of our techniques is, of course, there's nothing sound about these sort of machine learning based approaches. There's nothing complete about them. And so it's really difficult to make any formal claims about them. But at the same time, they generalize. Okay, they generalize, and they are not as performance heavy, because if you look at static analysis tools that folks have built, it's just, firstly, you have to define a property that you are testing for or you're trying to verify, and there could be umpteen properties, right? For each verification technique is designed towards a set of finite properties. So it's very, very compute heavy, and it also does not find bugs of these different categories. So I think both are useful, and I have made an explicit choice to go down this route because of, you can call these techniques shallow, but at the same time they generalize. So they're shallow and wide, but the verification techniques are deep, but they're narrow, in my opinion. But both are necessary.
Thank you.
I'll ask a couple of questions as well. One,
sure.
This whole configuration problem, how do you see it expanding or becoming even greater as we move to this whole cloud at the edge and this explosion we are beginning to see of IoT and cloud at the edge? How does this map into that scenario, and what are you thinking about in that context?
Yeah, great questions. It's just going to get hairier and hairier. I think techniques like this are just scratching the surface of the problem. It's going to be a great place for researchers, right, to solve these kinds of problems with all these IoT-based problems, especially in the area of security. And given that IoT devices are so varied and they have so many different characteristics, each one is different. And that just is a great ground, a fertile ground for building machine learning based approaches to solve configuration based problems for these, because they're so varied. And also because they're not tested, very often IoT devices are not tested as well as they could have been tested if they were, there was one central place where they were all being monitored, etc. So I think it's a great area. I think these techniques that I've talked about generalize, but at the same time, I think there's a lot more that needs to be done in this space.
Great. Thanks, Ranjita. There's a question on the screen. I don't know, Shashikant, are you able to bring in Deepika Karanji from PESU?
Sure, I'll bring her.
We could read it out, but it's nice to hear from her.
Good evening, ma'am. Thank you for the talk. I really enjoyed it. So I'm a student at PS University. Thank you. Yeah, so I just had one question. So like you said, Rex may not always provide the right suggestions, right? So it might have some false positives and things like that. So if you have some on-call engineer who kind of just accepts the incorrect suggestions by Rex and goes on to modify several files incorrectly, won't that lead to a lot more issues down the line? Do you have some kind of sanity checks in place to kind of deal with that?
Yeah, sorry, I have a phone ringing here, but I hope you can ignore it. The question, but the thing is, we give a very soft suggestion. We say perhaps you should just change file Y. Now, we considered saying you should change file Y in this way, and we can do that also, by the way. We can say change file Y in this particular way, add this particular code or this particular line to this file Y. We can do that, but we decided not to go down this route exactly for the reason the user experience has to be such that we don't sort of increase the problem beyond what it actually. We said just tell the user developer change this file and let them figure out whether to accept that or not. So they will look at that and they'll say, okay, how do I change this file? And then they will think about it, and then the change is manual. They'll change file Y the way that they want to, right? And so then it's on them if they make the wrong change. We don't really suggest exactly how to change it. So this problem has not yet happened because of this decision. But
okay, thank you.
KVS also had a question.
KVS has a question.
Yeah.
Hi, Ranjita. Great talk.
Thank you.
So
yeah, I
read
your question.
Sometimes we see.
Go on.
Yeah. Yeah. Sometimes we see that performance degradation happens. It's not like that there is an error in the system or something. So how have you looked at such cases? Want to comment on that?
Yeah. it's very difficult to do performance problems. I mean, we have looked at it in the past, though not in the context of Rex. So we have thought about doing performance analysis and configuration issues that actually cause performance degradation. It's something on it's ongoing work actually. So techniques like Rex do not really help there. So we need some way of tying back post-deployment telemetry to pre-deployment or commits, right? So we have some thoughts along those lines. It's just very difficult. We haven't yet made much progress. I'll go into a longer, half an hour answer maybe offline, but right now we are finding it. Yeah.
Okay, maybe one last question before we conclude this part of the session.
Yeah, I have a question. Hello?
Go ahead, Dr. Mohan.
Yeah,
we can hear you.
Hi, Ranjita. Very nice talk. It kind of brought the pragmatic aspects of trying to make DevOps work really good in the deployed world. So you're talking about this tool Orca and how it kind of possibly indicates what kind of code checked in and deployed could have triggered a bug. So its removal or taking the check-in out would help fix the bug. But wouldn't that in turn trigger?
Sorry, go on.
Sorry, can you hear us, Ranjita?
Yeah. Sorry. I just didn't want to disturb you again with the phone.
Okay. Yeah, Dr. Mohan will complete his question. Sorry.
Yeah, I just wanted to ask Dr. Ranjita that when you have Orca as a tool which kind of recommends that a particular check-in and deployment be rolled back, wouldn't that in turn, if that is executed, wouldn't that in turn bring back the bugs which the particular check-in and thing could have fixed? And wouldn't that cascade around uncontrolled?
Just so I understand the question, you are saying that if there is a let's say we make a mistake and we suggest some commit which was not the cause of the problem, maybe it was a fix for the problem, and we roll that back, then that could actually cause more problems. Is that right?
Because the latest version could already be a fix for some other problem, and now you're going back to that problem.
Yeah.
Exactly.
Yeah, that's true. And this actually goes back, I think also it's a very similar question to the one asked by Deepika. So we could actually be increasing the problem. But there again, the shallowness of our approaches actually helps. The fact that we are not really suggesting that, we're not saying, go ahead and revert this commit. We just say very softly, we say, these are the top 5 commits that could be the problem. You have to still go ahead and investigate. It's up to the on-call engineer to actually investigate. So we are not giving a panacea. We are just bringing down the number of commits they see from 300 commits to 5 commits, right? So then ultimately the onus is on the on-call engineer to find whether that's a bug fix or whether that's actually the cause of the problem. Even if they make a mistake after our suggestions, it's on them.
Very good. Mohan, is that okay? All right.
Yeah.
Good. Okay.
Keep things shallow. That's
keep it simple. So the human is what you're talking
recommendation
about. Sorry, go ahead.
Okay. Thank you.
So rely on human intelligence significantly.
Yeah, these are all just aids. We are not giving any replacement, but it's just an aid to the human. Yeah.
Sure. Okay, we are out of time and a great session. I see there is 1 or 2 other questions, but I request you to take that offline with Dr. Ranjita. And thank you very much, Ranjita, and look forward to having you be part of the CCM community in the coming years and participating even more.
Yes, definitely.
And thanks for doing it while traveling, and it all went smoothly. So great. Thank you.
I'm glad. Thank you so much for having me. Thanks specifically to both you, Gopal, and Sri Krishnan for running this, and KVS for inviting me and giving me this opportunity. Thank you.
Thanks a lot.
Thank you.
Bye.
You're welcome.
Thank you.
Thank you.
Krishnan, over to you to get the next session going.
Yeah, we end this session now and move on to tutorial session.
Okay.